moving right along here in Chapter 12, let's talk about the half-life. So scientists wanted a convenient way of describing the speed at which a reaction takes place, and that was slightly more convenient than just the rate constant, because truthfully the rate constant would work for this as well, but the rate constant is a bit more abstract. They wanted something more concrete, and the half-life is born. The half-life is the time that it takes for the concentration of a reactant that is involved in a reaction to reach half of its original value. So this is not the time that it takes for half of the reaction to be done. We are not saying that 2 half-lives and the reaction is over. We are saying that in 1 half-life, the concentration of reactants decreases to half of what it was before. The next half-life means would be where that new starting concentration then decreases by half again. So it's not half and then we're done. If you were to start at 1, half would put you at 1/2, another half-life would put you at 1/4, another half-life would put you at 1/8, and so on and so on. So we're going to have different half-life equations for first order, second order, and zero order, but we're really going to focus on first and second order half-lives here. Since the zero order, it actually is just 1 half-life and half the stuff is gone, and then the next half-life the other half is gone, since zero order is unique like that. But for first order and second order, it's not quite so simple. So for a first order reaction, the half-life, which is normally represented as this T sub 1/2, is equal to 0.693 over K. And if you want to look up the derivation for that, you can. I don't think that page number is correct, though. I think that is different in this new book. But regardless, the half-life is just a constant divided by the rate constant. This 0.693 is just the natural log of a half. So this half-life actually does not depend on the initial concentration at all. The only thing a first-order reaction half-life depends on is the rate constant. It's not quite as simple for second order, though. So for a second order reaction, it does depend on the initial concentration. Specifically, the larger the initial concentration, the smaller the half-life, which is to say the faster the reaction goes. So if you have a really small initial concentration, there's not as much stuff to react, and so it's not going to reach that half-life as quickly. And so it is different from the first order in that sense. But the equation is not too terribly different. So you can see here, for a second order reaction, the half-life is equal to 1 over the rate constant times the initial concentration. So neither one of those equations is terribly complex, but they are still very useful. And so then here the last one, the zero order. I think I might have misspoken just a little bit earlier. I think I said that it was just, well, actually I think that what I said earlier might still be true, but anyway, this is the equation for the half-life of a zero order reaction. I don't think we're ever actually going to use this again, at least not in the slides. You might come across it maybe in the homework. I don't remember, but like I said earlier, we're going to mainly focus on first and second order reactions, as those are more prevalent. But just in case you do come across it in the homework, the half-life for a zero order is just the initial concentration divided by 2 times the rate constant. Okay. So we have, I think, just one, I guess. One practice problem here to work through. So this is asking us to calculate the rate constant for a first order decomposition of hydrogen peroxide in water at 40 degrees C using this data. And I don't think we need any of the information here in this sentence. So we're trying to find the rate constant. And since we just got done talking about the half-life, it's a good bet to think that we're going to use the half-life equation here. But even if you did not know that, hopefully you'd be able to work that out. If this was just a random question from the homework, hopefully you could still figure out what's going on here, mainly by looking at these concentration values that we're given. So this is really the only data that we're given here, is the concentrations and the time at which we hit those concentrations. So if you'd notice, we start at 1, we go to a half, we go to a quarter, an eighth, 16th. So what we're seeing here is each of those half-lives. And so if we look at the time difference between each of these, it is a consistent time difference from one to the next, and that is 2.16 times 10 to the 4 seconds. So 21,000-ish seconds for each one of those. And that is our half-life. Because again, the half-life is just however long it takes for your initial concentration to decrease to 1/2 of what it was to start with. And that's what we have here. If you started at 1 and went to a half, we're decreasing by 1/2. All right. So then, if our half-life is 2.16 times 10 to the 4 seconds, we can use this to solve for k. So if we go ahead and plug in our half-life, say that is equal to 0.693 over k. We're going to need to do a little bit of algebra here. We'll multiply both sides by k, divide both sides by 2.16 times 10 to the 4. And let's see, what do we get with that? We get k is 3.21, we'll say, with the sig figs there, times 10 to the -5 per second. Sorry, that looks like -51. Let me redo that. So -5, 1 over seconds. So pretty slow. That is pretty slow. But that is the reaction that occurs in hydrogen peroxide. This is one of the reasons why we keep hydrogen peroxide in a brown bottle, because light actually catalyzes this reaction. It makes it go much faster. But even if you keep it in that brown bottle, over time, hydrogen peroxide does break down. And so eventually, if you've had a bottle of hydrogen peroxide in your cabinet for, 5-6 years, it's probably not a whole lot of hydrogen peroxide left in it. That being said, you should always still treat it like it is, like it still has all its hydrogen peroxide. Don't, grab it and, just pour it onto the ground in your backyard, because there's probably still enough in there that it's going to kill whatever you pour it on. Alright, so here we just have a nice little table for you to reference as you're working through the homework. So it gives you the rate law for 0, 1st, and 2nd orders. It gives you the units that the rate constant is going to have in each of those cases. It gives you the integrated rate laws, what you need to plot those integrated rate laws. It tells you what the relationship is between the slopes of those plots and k. And then it also gives you the half-life. So it's a nice little table to keep handy as you're working through stuff. All right, we'll call it there for this video. In the next one, we'll talk about temperature and the rate.